Hello everyone, and thank you for joining us for this webinar. We are excited to bring you this overview webinar on ETAP version 22.5, an integrated and continuous intelligence digital twin solution that's driving sustainability through the design, automation, operation, and optimization of electrical power systems. 2023 is a year of growth and transformation for ETAP. As part of the exciting new changes we are making to our company to better serve you, we're also aligning our software release convention with our new software portfolio. Moving forward, we will refer to ETAP releases based on the year of release, and of course, continue providing you with the version numbers as well, so you can be assured you didn't miss any of ETAP's valuable major and minor releases. So everybody, welcome to ETAP 2023. By connecting the ETAP Digital Twin platform to a larger ecosystem of complementary and collaborative solutions, we are enabling a transformative role for our customers to design, operate, and connect on a multidisciplinary scale. Harnessing the power of ETAP's ecosystem throughout the digital transformation process will help engineers, operators, and managers increase their awareness, understanding of power systems in a cost-effective and repeatable environment. And we continue to improve this transformation journey through ETAP 2023. Speaking of which, the release includes new solutions and features, plus hundreds of enhancements and time-saving improvements that support our customers with technology and best practices to design and operate power systems safely, reliably, efficiently, maintain compliance, and of course, drive sustainability throughout your electrical infrastructure. Through this webinar, and of course, given our limited time, we will showcase key improvements and the benefits of upgrading the software for your team and your customers. So let's get into the feature set itself. ETAP is improving safety for our customers and industry by ensuring we're able to model and analyze the latest in the line of mitigation measures is the ability to model, simulate, and analyze the impact of energy reducing line-side isolation devices such as ArcBlok. ETAP is continuing its mission to also bring compliance assessment tools by addressing an emerging industry problem driven by the proliferation of renewables, electric vehicles, and other technologies in the power distribution systems. Unbalanced networks and the ever-increasing presence of harmonics in the power network are also driving the need for more efficiency, minimization of unbalanced conditions, and therefore minimization of losses to improve the sustainability of power networks. Active harmonic filters are able to compensate for unbalanced condition and active harmonic cancellation in such situations. ETAP 2023 now includes detailed modeling of active harmonic filters, including vendor-specific models, taking the guesswork out of placement, sizing, and the effectiveness of these devices when distributed throughout the network. Zone Selective Interlocking, or ZSI, is a communication scheme used with electronic trip units for circuit breakers to improve the level of protection in a power distribution system. This is of course achieved through communication with the downstream and upstream devices in the network. Previous releases of ETAP already included the ability to model and connect ZSI wiring to simulate the impact of the logic in terms of protection and arc flash studies. ETAP 2023 now expands on that capability by visualizing the ZSI wiring on the single line diagram and ensuring that there are no gaps in the information needed by engineering and maintenance to safely commission and maintain these devices and the logic. Previous ETAP releases also included the ability to add user-defined fields in order for you to build and maintain an electrical maintenance plan in compliance with NFPA 70B and other local regulations. It allows you to also ensure the safe and correct commissioning of devices by including fields that are usually not part of a typical selectivity study, such as thermal settings for low voltage trip units. These user-defined fields can now be enabled as part of the ETAP data blocks, allowing you to print diagrams for engineering, operations, maintenance, protection as needed by simply applying custom data blocks with unlimited custom fields per asset. ETAP Unbalanced Load Flow Result Analyzer is a time-saving tool that compares and analyzes multiple unbalanced power flow reports in a single consolidated tabular view. You can compare the results of the general information about a project or more specific information such as the unbalanced load flow results for buses, branches, loads, sources, and of course it gives you insight into the impact of various what-if scenarios in one glance, allowing you to choose the best outcome for your power system. Peterson coil, ground fault neutralizer, or arc suppression coil. No matter where you are in the world, you know this device as an iron core reactor that's connected between the transformer neutral and the ground. And it's used for limiting the capacitive earth fault current, which is flowing at the time you have a line to ground fault. It also reduces the transient fault, which occurs due to lightning, and also helps minimize the single line to ground voltage drops. ETAP 2023 now includes the ability to model arc suppression coils or Peterson coils as part of the fault analysis studies, and also includes in effect in other analysis such as protection and arc flash studies. And finally, we have the ETAP License Manager, where we've not only upgraded our technologies to comply with the latest cybersecurity standards, but also added tremendous amount of improvement when it comes to license activation, especially when you're using a soft key or a keyless license along with your ETAP software. So let's get started with our first set of ETAP design solutions for simulation and analysis that are new in 2023. But before we begin, a few quick concepts just to make sure we're all on the same page. Let's talk really quick about time domain and frequency domain. Due to the ever-increasing number of nonlinear loads on our power distribution system, the existence of harmonics nowadays is inevitable. As a result, voltage and current waveforms are rarely sinusoidal. Harmonics is a form of course, waveform distortion that occurs in circuits that contain semiconductor-based electronics such as LED lighting, SMPS, electronic ballast, computers, robotics, test equipment, etc. These nonlinear loads, of course, impose higher frequency sine waves on the system, which result in more power lost in the form of wasted heat. The excess heat produced by harmonics can have a detrimental effect on the power system. Transformers, for example, are especially susceptible to damage caused by harmonics due to stray eddy currents that can circulate in the iron core and produce excess heat. Harmonic analysis is of course done using Fourier transform and other signal processing techniques that are used to analyze the impact of harmonics on the power system. And then again, very quickly, when we look at the time domain, each data point in time is represented in our waveform. The data is represented as a series of evenly spaced samples over time, collected at some sampling frequency, and then applying the signal processing techniques, we can go into the frequency domain using sine functions for each frequency. The data in this domain, of course, is represented as waves with particular strengths and phases at different frequencies. And of course, this method can also be used to reconstruct the frequency by doing an inverse Fourier transform. So let's take a look at this in action really quick. So let's visualize our harmonics through the Unbalanced Harmonics Vector Visualizer, which is new in 2023. What we're looking at is a perfect sine wave on my chart on the right hand side, And on the left hand side, we can see the vectors, which are perfectly balanced and 120 degrees apart from each other for phase A, B, and C. And just for simplicity, I'm showing you phase A for the waveform only. We can of course turn on phase B and C later on. And in terms of the harmonics, we have only the fundamental current. So of course we see a perfect sinusoidal wave. And let's go ahead and add a fifth harmonic into the picture. And let's say this fifth harmonic is perfectly balanced, and we can press on plot. And what we can see now is our ideal wave, sinusoidal. We can see our fifth order harmonic, and of course the resultant, which is the bolder line, giving us the combination of the fundamental and the fifth order. So this is how our waveform would appear in time domain. So we can take the ideal out as well as the orders, and this would be our time domain signal. And of course, for this time domain signal, we can of course see the corresponding spectrum as well. And as the amount of harmonics are increased in the system, let's say we have something further on the seventh harmonic as well, we can see there's further distortion of the waveform, and of course a additional seventh order spectrum that appears in our waveform as well on the right hand side. And then of course, as we move our vectors along, we can see very clearly how the unbalanced vectors remain the same, 120 degrees apart, but the corresponding vectors for the harmonics are also recomputed, and they vary quite substantially as the amount of unbalance in the system will also increase later on. So speaking of unbalance, let's look into the unbalanced network concepts really quick. So distribution systems, they're also quite often unbalanced in nature. And when I say distribution systems, it's not just utility distributions, it's just electric distribution systems in general. Disturbances or short circuits are usually amongst many reasons that result in an unbalanced system, but unbalanced system is more often caused by various factors that include unbalanced loads, unequal mutual coupling between the transmission lines, and then of course unbalance also occurs in three-phase power systems when single-phase loads such as lighting, office equipment, etc., they don't draw the same amount of current on each phase, resulting in greater stress on the neutral conductor. An ideal condition, of course, occurs when the loads are balanced, meaning that the voltage and current phases are exactly 120 degrees apart from each other, although the currents may not be in phase with the voltages, and that's of course due to the power factor. Motors, as an example, which are being driven by unbalanced voltages, have a smaller motor torque that lands up working in the opposite direction from the motor rotation. And this phenomena is typically known as a counter torque. And when this condition occurs, part of the energy delivered to the motor is of course working against itself, leading to more heat and more losses and more inefficiency that of course we should avoid. And of course, the concept of symmetrical components, such as positive, negative, zero sequence, enables the transformation of any desired unbalanced three-phase system into three separated symmetrical components so that we can analyze and quantify the amount of unbalance and assess the effect of unbalance in the network. So of course, let's take a look at this with our unbalanced harmonic vector visualizer and see the impact of unbalance along with the harmonics in our system. So in the unbalanced harmonic vector visualizer, we're also able to, of course, switch back to our waveform, show phase B, show phase C. So you can now see the effect of all three phases on the waveform as well. And instead of making sure that we have exactly balanced phases, we can also go ahead and change the balance on these phases in a more substantial manner, in a more appreciable manner. So you can see what happens to the harmonics in terms of its waveform. And then of course, we can also see what happens to the vectors with respect to the waveform. And we'll go ahead and of course change these magnitudes as well to have a significant impact on the vectors. So of course, as we rotate the vectors, we can see the different magnitudes of ABC phases. And then, of course, we can also see the impact on the spectrum as well. And of course, you're able to go ahead and do this for all different orders. So we can go ahead and change this correspondingly to something even more substantial, more exaggerated, if you may, just so that you can investigate what happens not only when the fundamental power supply is unbalanced, but what happens if you have tremendous amount of unbalance even in the harmonics themselves. And as you do so, you can see that the magnitude of the waveform, including its distortion, increases substantially. We went from nearly 15 to 20% distortion to almost 35% distortion by having unbalance in our harmonics. So the unbalanced harmonic vector visualizer, which is new in ETAP 2023, is just a quick means for you to investigate the impact of unbalance, harmonics, and a combination of unbalanced harmonics in a simple to use visualizer, also for educational purposes as well. But the main addition in ETAP 2023 is the unbalanced network harmonic simulation that includes a full three-phase unbalanced harmonic power flow along with the frequency scan. So let's take a look at the unbalanced network harmonic analysis in action on our single line diagram. Now for this demonstration, I'm using the example ANSI file that comes along with ETAP. So later on, if you like to play along and test drive these yourself, you can use exactly the same file without any other modifications. Of course, the balanced harmonic is available as a mode within ETAP, so you can run the harmonic load flow. And of course, we report the RMS voltages, the voltage total harmonic distortion, the current harmonic distortion, as well as the total power factor, displacement power factor, and so on and so forth. But for unbalanced harmonics, we've added a brand new mode into ETAP that uses unbalanced load flow as a fundamental enabler for the unbalanced harmonic simulation. And of course, when you run the harmonic load flow as expected, we display the phase A, phase B, and phase C voltages, as well as the voltage and total harmonic distortions. And you can also switch between all phases and all sequences. So you can also see the sequence values in terms of positive, negative, and zero sequence as well, including the THD's voltage as well as current. Now let's take a look at the DC system here that we have very quickly, and I'll go ahead and switch back into our all phases just to make it a bit easier to understand what's going on. And let's go ahead and copy and paste this load here. And what we'll do is we'll connect this load to our bus 2 and make sure that when we are utilizing this load, we create an unbalanced condition in our system. And this unbalanced condition will be, of course, substantially unbalanced on phase B. And let's go ahead and run our simulation again. And what you can see reported here is phase A, phase B, and phase C, which are quite substantially unbalanced, which I did on purpose. And you can, of course, see that the distortion on each phase is quite substantially different. When you run a balanced harmonic analysis and you compare with the assessment standards, they don't take this kind of unbalance into account. We're always looking at average values, and it's very easy to miss out on the fact that one of the phase unbalances can cause a very serious detrimental effect on your current harmonic distortion. And of course, notice what happens also to the voltage total harmonic distortion. So this is why it's important when you are running harmonic analysis in unbalanced systems such as university campuses, buildings, data centers, utility distribution systems, in general, any system where you know you're going to have an unbalanced, even railway networks for that matter, it's important to then switch over to an unbalanced network harmonic analysis to get a better assessment of the situation and size and determine the harmonic mitigation techniques appropriately. Speaking of sizing harmonic mitigation techniques appropriately, one of the other capabilities that we've added into ETAP 2023 is active harmonic filters. So let's take a look at active harmonic filters in action. So of course, one of the other harmonic mitigation techniques that we've added to ETAP 2023 is active harmonic filters. But before we look at active harmonic filter in action, let's go back really quick and look at some quick concepts for active harmonic filter. Electrical networks with poor power quality usually results in financial loss. There's environmental impact, and of course there's safety concern. And it's all stemming from the fact that harmonics produces excess energy, heat, and that excess energy or heat results in excessive costs for operation of the electrical system. And it leads, amongst others, to also frequent failures of equipment, reduced lifetime of the equipment, production losses, which of course indirectly also can affect the safety level of the installation. It increases the carbon footprint and also increases the chances of non-compliance with utility regulations. And there's also costs incurred due to extra kilowatt hour losses in typical network components such as transformers, cables, motors, and these losses are cascaded back to the utility power plants, resulting in increased CO2 emissions in general. Active filters are a good answer to these tough power quality problems caused by harmonics, load unbalance, and reactive power demand. Active filters can be applied to small, medium, or large applications such as buildings, energy chemicals, water facilities, general industry, data centers, and they provide harmonic mitigation, load balancing, and stepless reactive power control for inductive and capacitive loads. They can vary from several tens of amps to several thousands of amps, enabling an optimal solution for each type of application. And the ability to scale from several tens of amps to several thousands of amps is not by one individual harmonic filter, but by combining different master and slave units. So of course, through this, you can use them in low voltage and medium voltage networks. And they're fundamentally power electronic devices that are installed in parallel, typically parallel or in a shunt manner to the polluting load. It monitors the line current as well as the customer requirements that are programmed. And then it generates for each harmonic frequency a compensation current that is in perfect phase opposition to the polluting current. Very similar to noise cancelling earphones, the closed loop control system therefore measures the line current for each harmonic and reactive power component, compares this with an internal target that is set by the customer, and then any deviation is then injected and automatically eliminated. The selection capability of the individual harmonic components is usually a result of advanced control algorithms that are proprietary per vendor, and that's important to remember. And of course, there is typically a CT or a current transformer that's used to sense the harmonic current, with the control loop usually left in open mode if the CT is on the load side, and it's left in closed loop mode if the CT is on the network side. And this is important for adequate and correct harmonic cancellation. So let's take a look at what we've done in ETAP for active harmonic filters. So of course, we are providing the ability for digital twin modeling and simulation of active harmonic filters or power conditioning systems or PCSs. And we've included two models, a generic model and vendor specific active filters. And we've started with Schneider Electric AccuSign filters as our first vendor specific active filter. And our active harmonic filter in ETAP can establish harmonic targets based on current or voltage distortion. And it can also provide fundamental power conditioning based on power factor targets and load balancing modes. And it has the ability to automatically compute the harmonic injection that is required based on the location of our current transformer, as I discussed in the quick concepts. So let's take the active harmonic filter, apply it to ETAP, and see how it works in action. So coming back to our file where we ran our unbalanced harmonic simulation, let's adjust this file a little bit so that we can see how our active filter works. But we'll first see how this active filter works in an unbalanced condition only for fundamental current. So let's make this a bit of a reasonable unbalanced load on a low voltage system. So about 180 kVA of unbalanced load. And we want to, of course, switch over to our unbalanced load flow mode. Let's run unbalanced load flow first so we can see that we have around 85% power factor. We have a little bit of unbalance in our current. And let's go ahead and take this particular active filter and we set our power factor target of 90%. And let's go ahead and run our simulation again. And we can essentially see that when we run our simulation, we are nearly at 90% power factor using this particular objective. Could we achieve 92%? You can give it a shot and try it again. Bear in mind, we are at 130 amps per phase. And when you try to go higher than that, we have pretty much hit our limit of 300 amps. Because again, we are at 300 amps at 100% nominal voltage at 480 volt. And the voltage is not quite nominal. So we're able to go past 300 amps at a lower voltage. So 92% is not achievable, but 90% is. And of course, you can increase the size of the filter by putting another one in parallel to get more current to achieve a better power factor in terms of reactive power control. You can also activate things such as load balancing and unbalanced compensation. And though we are at the limit, the filter is going to do its best to adjust its per phase output to try to come and balance the unbalance in the system as best as it can, but it has pretty much reached its limit. But again, the point was to essentially show you that the active filter works as a power conditioning system in the unbalanced based modules. But of course, its true power is activated when we go to unbalanced harmonics. And in the case of unbalanced harmonics, again, we can put this filter out of service, run our harmonic simulation so we can see we have some amount of unbalanced harmonics as well as heavy distortion in the system. And first, let's turn on our passive filter so we can see what happens when you have a passive filter in the system. We'll create an output report for a passive filter, run our simulation so we can see that we dropped our distortion down to 12% by having a passive filter. And very quickly, if you did not have one, it was 18%, just as a frame of reference. So with the passive filter tuned, we can go to about 12%. So let's go ahead and turn this passive filter off again. And we'll go back to our active filter and turn the active filter on. And let's see what our active filter can achieve. And it's actually able to achieve and bring the distortion down to 2% based on this 300 amps. And the voltage distortion also drops down significantly. So the active filter in this case happens to be a generic active filter, but you also have the ability to choose a Schneider Electric PCS-N, which has a neutral wire or 4-wire system, or a PCS Plus. And using these filters, you can also achieve the simulation itself. And we use the proprietary logic that has been provided to us by the vendor to give you the exact response and output from that particular harmonic filter. Now, this is the steady state response of the active filter. There is a bit of a settling time that's usually involved as the active filter is engaged and it starts measuring, sensing, comparing, and then it starts injecting. So there is also a time domain feature of the active filter that we are also able to simulate inside ETAP. But first, before we do that, let me go ahead and bring up the plot analyzer. And then here we can compare our active and passive filter for, let's say, bus number 1, which is a bus upstream from bus 2. And we can compare our phase A, B, and C phases in terms of waveforms and spectrums. And of course, we saw our unbalanced vector visualizer, so you have an idea now between the time domain and frequency domain. So here we can see, for example, phase B as an example. We can zoom in here. We can see the baseline as well as the actual waveforms. So let me take the baseline out, and you can compare the active filter response versus the passive filter response. So of course the purple line shows a bit more distortion than the green line, but the true test comes in when we compare the spectrum itself. And you can see that the active filter reduces the distortion significantly on the lower orders, which is what we want. And the passive filter is not able to achieve that on either the lower orders or the higher orders in this case. So obviously not a fair comparison, but at least a comparison to give you an indication why active filtering is used to adapt to the electrical system versus a fixed tuned passive filter. And of course you can also combine these charts together, so you can see the ABC phases as well as the ABC spectrums together. And you also have, of course, the ability to switch between dark mode and light mode within these charts. All right, so that's the spectrum analyzer working with our unbalanced harmonics. And in order to see the time domain effect, we can go over to our study case, turn on the active filter in time, click OK, and rerun the analysis again. And you can see that we are running this analysis as a function of time. And again, what's happening is we are using the proprietary Schneider logic. We are reading the waveforms from the source. We are going through the proprietary logic, and we are trying to inject the harmonics in. So again, in the beginning, as function of time, the active filter doesn't do anything. There is no injection and no compensation. You can see the distortion is at 19%. But as the cycle moves on, you can see that the filter is able to achieve within 10 cycles a very, very good amount of compensation. In fact, the compensation happens within 2 cycles itself, and we've brought it down significantly to 3.3. The combination will give you a better indication of what is actually happening in the system. So let's just take bus 1, and we can also compare with bus 2 to see what's happening, and we can compare with the main bus as well, which is the point of common coupling. So let's go ahead and see what these charts look like for 3 different buses, not comparing with the passive filter, just the active filter case by itself. So we can see in our analyses, we can see significant amount of distortion that ultimately we can reset, and we can look at the resulting waveform, and we can see some of those spikes have been eliminated. So that's essentially the active filter working as a function of time, measuring, compensating, and then finally correcting the distortion on each particular phase. So again, there's a lot more detail behind what I'm explaining here, but hopefully gives you an indication of how the active filter works with the unbalanced fundamental modes as well as the unbalanced harmonic modes, which is new in ETAP 2023. Let's get to one more quick concept, which is arc flash instant energy. And of course, my goal is not to give you a full concept into arc flash analysis, but there are several ways to model and simulate arc flash instant energy reduction techniques in ETAP. There is zone selective interlocking, differential relaying, energy reducing maintenance switch, energy reducing active arc flash mitigation systems, such as creating a low impedance current path, light sensors using optical fibers, arc resistant equipment, and of course, now more recently in ETAP 2023, energy reducing line side isolation. So ETAP 2023 now includes the digital twin modeling of energy reducing line side isolation device, or ArcBlok, which reduces the possibility of having an arc flash by isolating the line side electrical conductors, and therefore limits the impact of the arcs and provides high-speed arc extinguishing response. So in your arsenal of arc flash mitigation, you have one more methodology that you can use to make sure that your systems are safer, you have enforced compliance, and reduce risk for your personnel as well as the equipment. So let's just see ArcBlok in ETAP in action. So in order to show you the impact of ArcBlok or line side energy isolation, we first switch over to ArcFlash and make sure that we are able to run a simulation here first. We get a warning message that's just letting us know that there's certain things that we need to take care of. And when we look at our simulation results, and just to avoid a lot of detail here, we'll take everything into the don't fault list. We'll go ahead and just fault this particular bus here and run our simulation. So we can see that our energy level for this particular breaker is level E, which is quite high, nearly 40 calories per centimeter square. And in order for us to see the simulation of ArcBlok, let's either switch to a revision, which is ArcBlok, or you can just simply pick up the scenario that we've created in the example file for 1584 ArcBlok. And when you select that simulation or scenario, you can simply run it. And when the results come back, as expected, if you have the ArcBlok capability on that particular bus bar or switch gear, the impact is quite substantial, it's quite dramatic. The instant energy drops to 1.2, which is very, very manageable, to level A. And we have safe energy levels here if you're doing any energized maintenance on this piece of equipment. So this is very quickly the ability of determining or including the effect of ArcBlok within ETAP. And then there is, of course, the study case itself that has the option to consider instant energy reduction using line side isolation that's available here. That's activated when the analysis is running. So that's ArcBlok in action in ETAP 2023. The Peterson coil, which is a new addition in ETAP 2023, first of all, very quickly, is an adjustable iron core reactor, as I mentioned earlier, connected between the neutral point and ground, and has the capability of producing resonance by tuning the inductance such that it matches the capacitance of the phases during a line to ground fault. It's also known as an arc suppression coil or a ground fault neutralizer, and it's there to prevent arcing grounds that can lead to over voltages on systems, especially with ungrounded neutrals. So during an earth fault, the arcing grounds are self-extinguished by the coil, and also in the case of sustained faults up to a certain degree, depending upon the rating of the coil. And it's able to reduce the earth current to a low value so that the continuity of the supply to the healthy phases is not interrupted. But typically the arc suppression coil is great at maintaining continuity of supply for temporary faults, and of course for sustained faults only for a short period of time, up to the extent of the rating of the coil, and the expectation is that the fault has to be cleared to avoid damage to the suppression coil if in case of a sustained fault. Now, the inductance value of the arc suppression coil is therefore continuously adjusted, monitored and adjusted such that if there is a fault current, IF, the inductance is able to exactly balance the capacitive current IC, creating a resonance ground. And that's the basic concept of an arc suppression coil. And of course, it's been used in Europe for the last couple of decades. So in ETAP 2023, you can simply model the arc suppression coil for the transformers, since it's part of the neutral, by adjusting the grounding type. So let's just see where this is available. Back to our ETAP software, we can select our one-line diagram. And in our one-line diagram, we can go to transformer T4, go to the grounding page and simply select Peterson coil. We can type in the resistance and the inductance value for the coil. And as soon as you click OK, we change, of course, the notation of the transformer grounding to show the inductance and the resistance in the star point or the neutral point of the transformer. And then if you want to run a simple simulation, we can go to short circuit, run the short circuit simulation, and we can see that based on the resistance and inductance that we have chosen, we are limiting the line to ground fault current to about 35 amps. So when there is a line to ground fault current, there's a very low amount of ground fault current that's flowing through the transformer that will not activate the healthy phases, and they can continue operating as before. And that basically is a very quick simulation of the Peterson coil in ETAP 2023. The arc suppression or Peterson coil can therefore be used for 2-winding transformers, 3-winding transformers, zigzag grounding transformers, and then it's able to automatically determine the ground fault impedance, the zero sequence that is needed to reduce the arc resistance and of course ultimately extinguish the arc itself. Now, zone selective interlock has already been present in ETAP for the previous releases, and the ZSI in ETAP 2023 is enhanced so that you can see the ZSI graphically. You can display the interlocks for the selective protected devices. You can see the interlocks in either a single or multiple single line diagrams. You can also customize the look and feel of the interlocks using the theme manager, where you can customize the output restraint signal, the remote interlocks, the terminals, in terms of the line style, width, color, fonts, etc. So let's see the ZSI wiring visualization in action in ETAP 2023. So we can simply move to our protection mode, and in the example ANSI file, we have given you a new view, which is a ZSI view, so we can bring that view up. You can press the home key actually to maximize and fit the diagram as best as you can. So that's a quick tip within ETAP. And then, so I'll bring up the ZSI manager first from the toolbar on the right hand side, and we can see CB22 and 23 are selected for ZSI wiring, but it's disabled. In fact, we can double check that. You can select CB22. We can see it's a ABB breaker, and this one's a Cutler hammer. And you can double click on CB22 to open up the editor, and you can see ZSI is actually deactivated or not selected in this particular revision. So what we'll do is we'll just switch over to ZSI off, and I just want to prove or show one point here in terms of the purpose of the ZSI. So here we can see that we have CB22 and 23 both tripping at the same time if you have a fault downstream of circuit breaker 23. And this basically means we don't have good selectivity on bus 1. If there were other loads connected to bus 1, this would not be an ideal coordination setup for us. So if we go to ZSI on and we go ahead and apply the same fault again, and in this case we can see CB23 is tripping first, then followed by CB22, which is being restrained by the ZSI wiring that we have applied. So this is now giving us better selectivity with the same settings that we have for 22 and 23. So the ZSI is impactful in terms of providing selectivity, as well as offering arc flash mitigation techniques in situations, especially for the low voltage systems. So let me go ahead and quickly reset here, and we can see our ZSI wiring visualization itself. So again, when I open up the ZSI manager, we can see in our revision these two are checked, and that's because I have my ZSI input and output terminals wired. They have been interlocked with the upstream device, and we can of course double click on the breaker itself, and we can make certain adjustments as needed. Now we have our input phase, which is phase or ground, and output also, which is phase or ground, and you can simply change those to phase and ground, as well as phase and ground here, and start making adjustments to your ZSI wiring. And whenever you see a phase plus ground, you have both options available as an input. And here we can see that there's also visualization showing that there's a self-restraint that's been applied for this particular device. Now, in case you want to change the visualization and the color styles, etc., you can simply go to the theme manager, which has a new page for ZSI, and change, of course, the customization for the box itself, the terminals, the remote interlocks, as well as the graphical interlocks in terms of the line style and line thickness. For example, if you want the phases to be thicker, you can set them to be thicker as such. And same thing for the ground wiring, the phase plus ground wiring, and so on and so forth. So this gives you very good control and flexibility. And of course, the ZSI wiring is saved along with the rest of the ETAP theme in the ETAP defaults. So you can easily navigate between different defaults that are saved for you for your particular diagram. So this is the new ZSI visualization on the single line diagram in ETAP 2023. Another amazing capability that we've added in ETAP 2023 is Unbalanced Network Load Flow Result Analyzer, which allows us to analyze multiple unbalanced load flow scenarios using Microsoft Excel. And this is a little bit of a different type of result analyzer because the data is directly output into Microsoft Excel rather than giving it to you in a visualization table. And all the comparisons are already done for you in Excel and already pre-formatted. And we know you will love this particular feature as soon as you see it. And one of the other things that it's able to do is it also allows us to compare the protected device loading compared to its pickup settings and ratings. So when you have a trip unit and you have a long time pickup on that trip unit, we are also able to compare the unbalanced load flow results along with the trip unit long time settings, and not just compare it with the breaker frame ratings, which can be different in many situations. So let's see the Unbalanced Network Load Flow Result Analyzer in action in ETAP 2023. So coming back to our diagram, I'm back in base mode and using our study view, and I want to go ahead and run a simple unbalanced load flow. So we go ahead and run our unbalanced load flow simulation. And in this particular case, we have certain results that are being shown or displayed on the single line diagram. And of course, as always, you can turn on or off certain pieces of information that you're visualizing on the diagram, just to make sure that you can see the information clearly. So we have ABC phases. We can clearly see this utility has slight unbalance. And we can switch over to an alternative configuration. Let's just choose stage 1. And we pick up a completely different output report, which is ULF, and run our simulation there as well. And here we can see things are perfectly balanced. We're actually exporting power to the grid. So completely different set of results. And now we can go ahead and bring up our unbalanced load flow result analyzer, compare ULF and UNLF results in terms of all of these different capabilities. And what the program quickly does is puts together the general information of what you're trying to analyze. It's comparing the sources, including the operating power across each scenario. And you can also compare the total source loading, the total load connected on various buses, and of course you can also filter different output reports from here, so you can easily analyze one or the other itself. Here we have our load totals, our branch wiring, which includes the overloads that have been determined in the system, as well as the branch totals as well from each scenario. This is the branch totals per phase. And we can continue on also looking at our control schemes. This is basically the voltage regulators that are in the system. The protected device alerts, which is basically the loading with respect to the pickup ranges or the long time pickup ranges for each low voltage breaker or low voltage trip unit. And you can also see a final summary of the total system demand and generation across different scenarios, and you can see how the losses vary from one scenario to another. So again, it's a very typical load flow result analyzer, but this one is unique in the sense that it's comparing each phase with respect to each other. And it's also able to compare the low voltage pickup settings with respect to the alert settings that you have for your unbalanced load flow. So it will let you know if your protected device will trip on long time, not just based on the frame rating of the breaker. So this is the unbalanced load flow result analyzer in ETAP 2023. The ETAP license manager is now quicker and more reliable in terms of ETAP license management, with over 30 enhancements applied towards improving our cybersecurity profile. And we've done that through changing our complete foundation to harden it against common vulnerabilities and exposures on a proactive basis. And this allows us to not only have a new improved cybersecurity profile, but a more reliable automated license key exchange system for easier and effortless installation, especially for our keyless or soft key licenses. And we've obviously made sure that the ETAP license manager can be installed and present alongside other licensing services as well. If you're using the hardware key, you can go ahead and upgrade to the new ETAP license manager. If you are using the software key, you can continue using the existing license manager, but you need to contact us in order to upgrade to the new 22.5 license manager. And the need to do that is because we want to make sure we deactivate your existing software license in a proper manner. We install 22.5 license manager and we can reactivate your soft key license. So watch out for a note from our sales department for more detailed instructions. And we know you will love this new ETAP license manager, especially when you're using the USB as well as the software keys. Cable systems are also enhanced. The very first one is the enhancement to the cable manager with expanded reporting capabilities. And in order for these expanded capabilities, we can go back to ETAP very quickly. And in our ETAP software, we can launch the cable manager. And in terms of the ampacity calculation for these cables, we can expand and view the new fields that are provided, allowing our users to easily compare the derated or the adjustment factors that are being used to size every single conductor. So this avoids the need to open up every single editor to see what adjustment factors were being used when sizing these particular cables. And of course, we include the comprehensive tabulation of the protection, the overall sizing results from the phase conductors, protective earthing, neutral conductors, as well as the shock protection, and of course finally the summary as provided by the cable manager. So the ampacity columns have been expanded significantly to include these new derating or adjustment factors. We've also added the ability to handle more than 9 cables per conduit per location. So this means that when you are performing any kind of simulation for underground raceway systems, you can easily go and add more cables per location, up to 9 cables to fill up a particular conduit. And this is very much possible when you have large data centers in dense areas, in dense urban areas, and a lot of cables are compacted in a small amount of space. And or of course you have power distribution systems for utilities where you can again have high density cables being routed through urban areas. So you can easily take new cables and add them into these locations, and you can essentially double click and keep going till you have more and more of these cables included per location. So this capability has been added to ETAP, and of course, as you notice, the location size keeps expanding automatically to accommodate these cables. And of course, you can continue using these features that show you the dimensioning to better adjust the location of the cables and make sure that you have a good fitment of the cables within the raceway or the location. We've also enhanced our controllers. These controllers are used to manage renewable energies such as energy systems like microgrids and large-scale renewable power plants. And these controllers are used during simulation to make sure that you're able to take into account the logic from the controllers that are typically installed during commissioning phases, and make sure that by using the controller logic in design, you are able to optimize the design further and save cost on costly oversizing as well as undersizing that could happen when you are designing these types of electrical systems. And we continue enhancing our intelligent controllers by adding even more black box DLLs and more automatic parameterization of vendor specific models. So we encourage you to contact us to discover more about our intelligent controllers, which are then able to model not just the microgrid controls, but also STATCOM controls, power plant controls, and they also are used for grid code analysis as well as operator training simulators. We've also expanded our ETAP API, which is a RESTful API for interoperability, allowing us to have a secure HTTPS connection to Data Hub. And we've also implemented a Python client, of course, using ETAP Py, which you can use to run scenarios and studies and get all the project data from your tools. ETAP Py, which is the scripting and the study automation aspect of ETAP that uses the Python scripting language, includes the ability to run ETAP studies remotely and in parallel across machines. And then of course it includes detailed reference documentation such as the example code, descriptions, etc. And of course we've added more enhancements to the API as well as the scripting capability. We also continue enhancing our DataX that helps us accelerate digitalization by allowing our users to move to ETAP and move away from legacy and obsolete tools such as SKM Power Tools, Power Analytics, by improving the way that we do the conversion from these devices. And then of course we've done also a lot of improvements in terms of conversion from Easy Power to ETAP as well, including the ability to handle more components and better one-line diagram placement and layouts as we do these conversions. The engineering libraries, which are our verified and validated equipment libraries, have also been expanded in this version to include even more cables, more reliability data, as I've discussed earlier, from 493 and 3006.8. And of course, with unbalanced harmonics, we've added new unbalanced harmonic sources that include current and voltage sources as well. And then of course, in our modern internet-facing applications, we take into account very seriously the topic of cybersecurity. So of course, we've changed our complete foundation for the ETAP License Manager to be more compliant. But the ETAP application, NetPM, which is used for network project management, the ETAP real-time SCADA HMI viewer, and the web browser-based dashboards or the thin clients, they all have upgraded cybersecurity compliances. And we continue to bring cybersecurity into our development cycle as we move forward into the future releases. So that brings us to the end of this particular webinar because of constraint and time. But of course, we have a complete webinar series for ETAP 2023 that you can join and go into more details into each of these capabilities. And we're excited that you can, of course, go ahead and download ETAP 2023 from our website, which is now a released product. And we are, of course, excited about this new chapter that will help increase productivity, collaboration, and efficiency, and of course, enable the energy transition journey for our customers. And of course, we look forward to continuing to serve you with the same level of quality and excellence that you expect from ETAP. And as again, a reminder, ETAP will continue to operate as an independent software company, and we will continue delivering value as a vendor agnostic solutions provider with our expanded and broad new portfolio that includes, of course, ETAP software, C, advanced electrical design for Revit, and Canical. Thank you, and we look forward to your questions.